Hi all. This video lecture we will discuss about what is pipelining, the basic concepts of pipelining, and what is a data dependency and how it can be handled. Okay. So let me start with what is pipelining. So when I say pipelining, we are going to execute more than one instruction simultaneously. So why do we need to execute successive instruction is to improve the performance. So to speed up the execution of the processing, so either you can use a faster circuit technology, or we can arrange the hardware in such a way that more than one operation can be performed at the same time. So here in pipelining, we are going to make some arrangements in the hardware in such a way that we can perform more than one instruction execution at a time. Okay. So, in general, a typical definition of pipelining is an effective way of organizing concurrent activity in a computer system. So let me take a 5-stage pipelined processor. So the first stage is fetch, second stage is execute, third stage is compute or second stage is decode, and third stage is execute or compute, and fourth stage is memory, fifth stage is write. So you can also take maybe a 2-stage or 3-stage. So here I have taken an example of 5-stage processor. So when it comes to a pipelined execution, you can look at the figure here. So you have 3 instructions, say for example, ij, j plus 1 and j plus 2. And in the first clock cycle, the first instruction is fetched. And in the second clock cycle, the first instruction is moved to the decode stage. By the time the fetch unit is free, so the fetch unit is fed with the next instruction. Similarly, in the third clock cycle, you can see the first instruction is being executed in ALU. The second instruction is being decoded in the decode unit, whereas the third instruction is being fetched in the fetch unit. So at a time, in this case, we can see 3 instructions are executed concurrently. This is what we say it as pipeline. Okay. So here I have taken 5 stages. So this is the organization of a 5-stage pipelined processor. So as you all know, in between each and every stage, you will be having a buffer. We say that as interstage buffer to have the intermediate results. So as I told you, first step is fetch, then followed by the decode, and third is you can have fetch the data from the register file, then fourth is compute, then memory access, and finally storing it into the register, right? Okay, in between you have n number of interstage buffers. So this is the organization of a 5-stage pipeline processor. As we are doing concurrent execution, there are many conditions that will make a pipeline to stall. Stall in the sense wait. Okay, so this situation we say it as hazards. So the condition may be the data may not be available, which we say it as a data hazard. Sometimes the instruction itself may not be available for execution. We say that as a control hazard. And sometimes there may not be enough resources. Okay, we say that as structural hazards. So there are different conditions which may make the pipeline to stall. That is to wait. That we say it as a hazard. So in this video lecture, we will see what is a data hazard, what are all the situations will bring a dependency, and how it can be handled. Okay. So let us take this example. You can see there are 2 instructions, add and subtract. So here we R2 is equal to R3 plus 100. We are taking an immediate addressing mode. Here the constant value is added with R3 and it is stored in R2. Then subtract R9, R2, 30 is, so in this case, the second instruction need to wait for the data from the previous instruction. So after adding R3 and 100, then this data R2 from the register R2 has to be fed on to the subtract instruction. So you can look at the diagram here. So in the first clock cycle, we will be fetching the first instruction, and in the second clock cycle, the first instruction will be into the decode unit by the time the second instruction can be fetched. Okay. In the third clock cycle, so you will be performing the arithmetic operation, that is R3 plus 100, and when your data R2 will be available is after the write operation. Only in the clock cycle 5, you will be having the data R2, and only after that you can perform the second instruction, that is R9 is equal to R2 minus 30. So R2 data will be available only in the fifth clock cycle, but you can perform the decode in the third clock cycle itself. So in this case, the pipeline has to stall for the data. So only you can perform the computation subtract operation in the seventh clock cycle, because the data will be available only in the fifth clock cycle. So decode will be completed in the sixth clock cycle, and we can perform the subtract operation only in the seventh clock cycle. So here the data is not available at that particular clock cycle. So this is what we say it as data dependency. So this is one scenario. So how to handle this data dependency? How can we reduce this waiting time? There are two approaches for handling the data dependency. One is operand forwarding and other one is NOP. Okay, that is no operation instruction. So by using NOP instruction, we can only handle the data dependency, but we cannot reduce the stall time. Whereas in case of operand forwarding, we can reduce the waiting time. So let me explain you how this operand forwarding works. The same example I have taken. The first instruction is add. So after the compute stage in the clock cycle 3, the data will be available in the temporary register, not in R2, but it will be available in the temporary register, maybe R, Y or Z. But only in the fifth stage, the data will be available in R2. But we have the results in a temporary register. What we can do is we can perform an operand forwarding by adding some additional hardware to the processing unit. What we can do is we can fetch the data from the temporary register and we can pass on to the next instruction so that we can save the waiting time. Even if not 100%, to some extent we can reduce the waiting time. Later on in the fifth clock cycle, it can be written into the actual register file R2. But the temporary register RZ will be having the value and that can be fed on to the next instruction. So this is one way of reducing the stall time and handling the data dependency. This is the best way. And this is the hardware. So in addition to the existing hardware, here you can notice we have included another multiplexer to fetch the data from the intermediate register, that is RZ. From RZ, what we can do is we can fetch the data from the temporary register, and using a multiplexer, you can feed on to the ALU for executing the next instruction. This is a simple, slight variation in the hardware. We can achieve the data, we can reduce the stall time. The other way of handling the data dependency is using a no-op instruction. No-op means no instruction. So using NOP instruction, we can just intimate the compiler that there is no operation being performed for the next 3 clock cycles, so that the compiler will not fetch a wrong data. This is one way of handling the dependencies using a software. But what is the disadvantage of using this methodology is the code size will be increasing. So how many clock cycles it has to wait, that many number of NOP instruction has to be included. No op instruction has to be included, so that the code size will be increasing, and also the stall time will not be reduced. Whereas in case of operand forwarding, we can reduce the stall time. This is only intimating the compiler that it has to wait for the data for the next 3 clock cycle. This is only a way to handle the dependency and not to reduce the cycle time. Okay.